This is Physics 104A at Porterville College, Chapter 13. Homework, starting with number 19. Write an expression for simple harmonic motion, and Part A says amplitude 10 centimeters, frequency 5 hertz, maximum displacement at t equals 0. It helps to draw it, see what it looks like. When you see maximum displacement at t equals 0, you see this is a cosine curve. So it's best to use a cosine function. So we have x of t equals a cosine omega t. That's the general form of simple harmonic motion. We need to find omega, so omega is 2 pi times the frequency, which is going to be 2 pi times 5, or 10 pi. So here we have the function x of t equals 10 centimeters, the amplitude, times cosine of 10 pi t. Part B. Amplitude 2.5 centimeters, angular frequency 5 radians per second. Now, you have to pay attention to that word angular frequency. That means omega, so it's going to be radians per second. Maximum velocity at t equals 0. So maximum velocity at t equals 0, one way you can think of that is that's where the slope is maximized, and that looks like this. And you can see that that is, sorry, this horizontal axis should have a t here. Okay. You can see this is a sine curve. Now you could model it as a cosine curve, but it's just easiest to model it as a sine curve. So x of t equals a sine omega t. Therefore x of t equals 2.5 centimeters times sine of 5t. Number 25. We have a spring and mass system. Undergoes simple harmonic motion, gives its maximum acceleration and its maximum speed, and determine various values. Okay, so here's the setup. It's going back and forth horizontally. There's the mass of 50 grams, maximum speed, maximum acceleration. Here is the formula for speed. V equals negative omega a sine omega t, and that comes from the derivative of the position function. So the maximum of that, you're looking for where this is at its extremes. That's where sine of omega t is going to be either 1 or negative 1. We really care about, we don't really care whether it's going to the left or to the right, so that's why I take the absolute value. Whether it's positive or negative, the maximum speed is omega a. The acceleration, here's the acceleration function. It's the second derivative of position. Negative omega squared a cosine omega t. It's going to be at its extremes, at its maximum, when cosine omega t goes to 1. And again, we don't care if it's negative 1 or 1. We're looking for the maximum absolute value, regardless of whether it's going to the left or right. So that's why I take the absolute value. And that's going to be omega squared a. Now, one way you can find omega is to recognize you have the acceleration maximum divided by the velocity maximum, omega squared a divided by omega a, and that'll give you a value for omega. So we can say omega is the acceleration maximum divided by the velocity maximum, 15 divided by 3.5, and we get, and here's it rounded off, 4.3 radians per second. B asks us to find the spring constant. So K equals m omega squared. We already found omega in part A, so I get 0.92 newtons per meter. C asks us to find amplitude. Well, given that we have values for maximum acceleration and maximum velocity. Here's something we can do. If you take the maximum velocity and you square it, remember it was omega a, but you squared and it's omega squared a squared. Divide it by the maximum acceleration. That should be absolute value right there. Omega squared a. You divide those and you're left with the amplitude a. So a becomes v squared over a. 3.5 squared over 15, that gives 0.82 meters. Okay, 28, probably the easiest of this set. How long should a simple pendulum be? So its period is given by the following. Okay, so here's the relationship between period and length. We want to solve it for length. So length equals g times the square of t over 2 pi. So I've just plugged in the various values for t. Here's 200 milliseconds. And it gives a length of 0.0099 meters. And I just converted that to 9.9 millimeters. A period of 5 seconds would be 6.2 meters. Period of 120 seconds would be 3,575 meters, or 3.6 kilometers. Number 31 involves a physical pendulum. A meter stick is suspended from one end and set swinging. Find the period of the resulting small amplitude oscillations. By the way, this is something you could experimentally do at home if you have a meter stick. And when we get the result, you can see if it actually works out. So for a physical pendulum, you look at the diagram here. Here's the meter stick. There's the pivot. What's going to be of concern to us is L, which is the distance from the pivot to the center of mass. And that is 1/2 the length of the meter stick. I've called the entire length of the meter stick L naught. So that's L is going to be 1/2 of L naught. Period is 2 pi over omega. And omega for a simple pendulum, here's actually it inverted because we're dividing by omega. So square root of I over mgl times that 2 pi. For a rod that's being rotated about one of its ends, as is the case here, we get this from chapter 10. I equals 1/3 m times the length squared. And I'm using L naught squared because it's the entire length of the meter stick. And now we plug these things into the period equation. So 2 pi, I've made I to be 1/3 ml naught squared. mg times L, and L is this distance here, that's going to be 1/2 L naught. So you clean that all up and it becomes 2 pi times the square root of 2 L naught over 3g. Plug in all the numbers where L naught is 1 meter, g is 9.8 meters per second squared. Remember to take the square root, and you get a period of 1.6 seconds. All right, number 43. A mass slides along frictionless horizontal surface at speed v0, strikes the spring. After an elastic encounter, it heads back in the direction it came. In terms of k, m, and v0, determine the amount of time it was in contact with the spring and the spring's maximum compression. All right, well, one thing you can do, here's where I would start. Consider what is the energy in the spring. The energy in the spring at any time of its compression is going to be 1/2 k times how much it's been compressed, 1/2 k a squared. Now I call a the amplitude because we're actually looking at this spring as it compresses and then comes out. That is actually half a period of oscillation. So kinetic energy, conservation of energy says that the kinetic energy that the mass had before it came into contact with the spring is equal to the spring, its elastic energy at maximum compression. So 1/2 mv naught squared equals 1/2 k a squared. By the way, I've set this up as a position versus time function. So we're imagining that the spring, again, it's in oscillation. Now it only oscillates for half a period, but this is where it is when the mass hits it. It presses down to -a, and then it comes back up and the mass leaves it. So we're looking at an upside down sine curve. And we want to know what is this value of time when it comes back up here, when the mass finally leaves it. Well, going back up to our conservation of energy equation, we can solve this for A. A is equal to V naught times the square root of m over k, where V naught is the speed the mass was going at. Well, setting this up, if we see that we're looking at part of an oscillation, again, just half a period, but that it's an upside down sine curve, let's set it up as a position function on a sine curve. So x equals, it's upside down, so I've made it -a times sine omega t. And what I'm going to do is I'm going to solve for this t. Solve for the time where position is equal to 0. Now we should get two results. Here, time is equal to 0, and we want to know what is this time. So we set 0 equals -a sine, remember, omega is square root of k over m times t. And so we say, where is a sine function equal to 0? Well, it's equal to when the argument is 0, when you're taking the sine of 0, also when you're taking the sine of pi. So this argument, the value or the expression that's in the parentheses, is either equal to 0, and here I've set it equal to 0, or it's equal to pi, here I've set it to pi. So when we solve for t, we get t equals 0, that's this point here, that's just where the mass originally hits the spring. And then we get here pi over square root of, or pi times the square root of m over k. And that's this time that we were solving for. Now, here's actually a simpler way to solve for that same solution. Period is 2 pi over omega, and omega is square root of k over m. We recognize that if we think of this as an oscillation, the contact time was half of the period. Let me scoot this down so you can see the picture. Remember right here, this is half of a period. So, contact time is half the period. Half of t equals, you can have 2 pi over 2 omega. The 2's cancel out. We have pi over omega, and we have pi over, or pi times square root of m over k. Same result we got up here. Okay, number 50. Oscillation in two different directions. It's going to bounce up and down. It's also going to be a torsional oscillator. And we're looking for, in terms of k and kappa, what value of disk radius will give the same period for vertical and torsional oscillations of this system. Okay, omega vertical equals square root of k over m. The torsional omega is square root of kappa over I. For a solid disk, I equals 1/2 mr squared. You get that from chapter 10. So we're going to set these two equal to each other. So we get square root of k over m equals square root of kappa over I. I've just squared both sides, so k over m equals kappa over I. And we want to solve for radius. So k over m equals, let's see, okay, so I, we're doing 1/2 mr squared, so 2 kappa over mr squared. A value of, or a power of m goes away. We solve for r, and it's the square root of 2 kappa over k. And I just show this off to the side dimensionally. Kappa is in Newton meters, k is in newtons over meters. So within the square root, you're going to get meters squared, and you take the square root, so dimensionally it works out that you're getting meters. Excuse my adjustment. Okay. Number 53. An object undergoes simple harmonic motion in 2 perpendicular directions. And there's the function. I've broken it down into scalars so we can just work with the x and y separately. A sine omega t in the x direction, a cosine omega t in the y direction. Show that the object remains a fixed distance from the origin and find that distance. Okay, so if you look at the picture here, what the x value is showing is that it's going back and forth like this, from a to negative a. The y direction shows it's going up and down like this, from a to negative a. Now that in itself doesn't mean it's circular. It could be doing a figure 8 deal like this. It could be, who knows, doing something like this. But we want to show that it's always going to be a fixed distance a, and it's going to travel in a circle. So part A says to find the distance. Okay, r equals square root of x squared plus y squared. Plug in those values, a squared sine squared omega t plus a squared cosine squared omega t. You can factor out a squared. Goes out to the side is just a. You're left with sine squared omega t plus cosine squared omega t. That's a trig function, which becomes just 1, and we're left with that a as the fixed distance. So it is circular motion. Part B, find an expression for the object's velocity. Well, its velocity in the x direction is derivative of x with respect to t. So you go back up to the position function and you get omega a cosine omega t. Velocity in the y direction is dy dt, so take that derivative and it's negative omega a sine omega t. So here it is in this burgundy box here, the vector notation. Omega a cosine omega t I hat minus omega a sine omega t j hat. Part C asks to show that the speed is constant and find its value. Okay, let's find the speed. V is the square root of vx squared plus vy squared. So I'm taking these values, the x and the y, and squaring them. So the x value becomes omega squared a squared cosine squared omega t. The y value is negative omega squared, so the negative will get squared as well. A squared sine squared omega t. And what you'll get is the omega squared a squared. They will factor out to the outside of the radical. What's left in the radical is cosine squared plus sine squared. That'll go to 1. And we're left with a constant speed of omega a. D says find the angular speed of the object in its circular path. I've written out the word angular speed here because omega has already been assigned. Omega has to do with the period of oscillation along the position and x position and y position. So let's just write it out as angular speed. We know that that equals v over r. Now, we plug in values. We know what V is. We solve that in part C. We know what R is. We solve that in part A. So omega A over A. And it actually does come out to be omega. Number 78, a physical pendulum. A disc of radius r is suspended from a pivot point. For what pivot point will the period of this physical pendulum be a minimum? So here is, for a physical pendulum, period equals 2 pi squared of I over mgl. And we're going to minimize it, meaning take its derivative with respect to L, set it equal to 0, and see where L is. Here's the diagram. I've set it up where there's the center of mass. L is somewhere along here. I've just made it an X right there. And we're trying to solve for it. What is that appropriate distance L that will minimize T? Well, we need to know, if we're finding T, we need to know what I is. So let's use the parallel access theorem. I is the the moment of inertia as it's being rotated about the center of mass, plus md squared. So if we're rotating it about this pivot point, I is going to be, for a disk rotated about its center, 1/2 mr squared plus ml squared, because L is the distance from that center of mass. Plugging that into the period equation, we now have down here 2 pi times square root of, and for I in the numerator, 1/2 mr squared plus ml squared, and the denominator still has over mgl. I've cleaned it up a bit. Mass divides out, and we're left with, in the radical, r squared over 2gl plus L over g. So this is the period function. What we're going to do now is take its derivative with respect to L, set it equal to 0. So here's the work I did. The derivative, the first thing I did was take the function whenever I have to take the derivative of a radical, and put it to the 1/2 power. So the derivative then is, if you think that to the 1/2 power, 1/2 times 2 pi becomes just pi, times the radicand to the negative 1/2 power, times the derivative of the radicand. Now if we're setting it all equal to 0, just basic rule of algebra, one of these things has to be equal to 0. Pi isn't going to be it. Something to the negative power is not going to be equal to 0. So it's this part here that must be equal to 0. So I'm not going to worry about these parts right here. It's just I know that this part has to be equal to 0. So let's take this derivative. So ddl of what I've got over here, notice I've rewritten it slightly. The L, I've put L to the negative 1 power. That's just how I do the derivatives. And what you should get for that derivative is negative r squared over 2gl squared plus 1 over g equals 0. I've divided the g's out right here, so negative r squared over 2l squared plus 1 equals 0. And I solve for L, and it's r over square root of 2, or about 0.71 times r. So let me go back up to the picture. So if the r is the radius of the circle, it's actually about where I've put the x, 71% of the way up there. Scoot it back to the solution now. That's it for the Chapter 13 homework.